tell you a little bit about myself and my journey to where I am, and I want to tell you sort of about my path and how I got there and sort of what my career is, and then I want to tell you a little bit about the science I do today, just in one slide or so. Let me get this going. I have the gift for gab, so to speak, so I'm going to set a timer for myself because Dave, who's going after me, has got some amazing things to show you guys, and I really don't want to improve on that endeavor either. So I went to high school in Wisconsin. I thought we'd go back to there. Actually, we can go back to the upper left photo. That little puppy in the upper left is Bandit. It was my childhood dog, and I named it such because it had that really weird black face, and it kind of reminded me of like a little mask, like the old cartoons of like the train robber, and so that's how it got its name. That was me living in Tulsa, Oklahoma at the time. From there, I moved to Wisconsin and ultimately went to Appleton High School West. I was a big fan of sort of chemistry, and I had actually, believe it or not, a water rescue and scuba diving class in my high school. I don't know if you guys have something that fun, but I spent a lot of time loving that. Thought I would be a biochemist, so which is the reason I went to the University of Wisconsin. I had this idea that I would become a biochemist, and they had one of the top biochemistry programs in the country. And because I'd graduated from a high school in Wisconsin, I could get in-state tuition. And so I went there to be a biochemist. As I'll show you in the next slide, it didn't take long before I actually switched to a sort of a double major. And then ultimately, I never finished that biochemistry endeavor. My first job, mowing lawns. By the time I was in college and high school, I actually had a small landscaping company where I employed a number of people, and that helped pay for me to go to school. Extracurriculars, I was a multi-sport athlete, mostly soccer and track, but also played basketball. Spent a lot of time doing judo, loved water polo, and did some young entrepreneurship stuff. I went to undergrad at the University of Wisconsin-Madison, and I majored in mechanical engineering. As you can see, it doesn't match the biochemistry label at the top, and I'll get into that in just a minute. Did a number of extracurriculars there. Spent a lot of time just hanging out with my friends, but played basketball and also started to develop a judo and jiu-jitsu club there, and ended up running that club for 10 years. I also went to graduate school at the University of Wisconsin after a short stint in Chicago, working in polymer engineering, and then a fellowship in cell molecular cancer biology that I'll talk to you guys a little bit about later. So it's an odd track for an engineer. In the early 2000s, cancer wasn't really being explored on the molecular scale and cell scale from an engineering perspective. There was technology being built. You can think about medical imaging and things like that. But the idea of what we call now cancer bioengineering was new. In 2012, I became an assistant professor here at the University of Minnesota, which brings us to the bottom. Now I'm an associate professor here with tenure, and I work on cancer. So my entire lab studies cancer progression and trying to understand the physical mechanisms that allow cancer to move through the body and develop novel therapeutic strategies to get at it. I still do judo. I am a CrossFit nerd. I like to snowboard, and me and my family are crazy about games. So with that said, as I told you that slide, it might seem that my journey looked something like this. I went from mechanical engineering to biomedical engineering to a biomedical engineering Ph.D. to cancer research, and it's just been this really straight linear path for me. And nothing could be further from the truth, actually. My path, even in a simpler form, looks more like this. All right? So I started off thinking, oh, okay, I'm going to become a biochemist, so that actually is why I chose Wisconsin as opposed to some of the other schools I was accepted at, including one in sunny Southern California. I was like, oh no, I want to be a biochemist. I should go to the Midwest and stay in Madison, which turned out to be a great experience for me. I ended up switching to mechanical engineering only one semester into school. And actually, for a long time, I was a double major in mechanical and biochemistry. Actually, I'm 6 credits away from a biochemistry degree that I never finished because I didn't see the need at the time. Yeah, 6 credits, I know, right? 2 classes. Sidebar. The 2 classes I didn't take, one was actually a chemistry class. It was a second semester of organic chemistry with the lab. The other was an English class. There was a weird elective rule that came into play around my senior year, and they said, if you want to get a biochemistry degree, you got to go take this class in English. And I couldn't quite wrap my brain around that logic. And I had a job offer, and so I just got the mechanical engineering degree and moved on. At the time, though, I thought I might go to med school. That was sort of plan A. And I started shadowing hospitals and doctors and things, and just realized that wasn't for me. There was a number of reasons why. The biggest one was I liked solving problems more than implementing them. I liked understanding why things had happened, and it seemed in the clinic it was more implementing the knowledge, and I wanted to develop the knowledge. In a way, I thought I wanted to spend more time maybe writing the textbook than reading it. So I took a job, actually, for a while. The question mark was, yeah, I did that, but for a very short period of time. So then it led to grad school. I entered a master's degree in engineering physics. that led ultimately to a master's degree in biomedical engineering, and I was certain I was going to get a job or go to law school afterwards. I started applying to jobs. One was Medtronic here in the Twin Cities. Had an offer from them on the table, as a few other places. My roommate at the time was in law school, and I thought, that seems super cool, and all this patent law stuff, and it seems great, I should do that. And he convinced me not to, and then he went on to become a quantitative political scientist at Harvard. And I still look at him funny. Remember that advice you gave me about not going to law school because it was so boring, and now you have this really exciting job in law? Actually, if you read the New York Times and things, he's an expert on quantitative political science in the Supreme Court, and a lot of the colorful things that have happened over the last couple of years. He's been quite prolific in writing about them. So if you ever see articles by a guy named Ryan Owens, that was my college roommate who talked me out of going to law school. He's somewhat famous. Me, not so much. Maybe if I'd have gone to law school, I don't know, who knows. So I ended up switching to a Ph.D. in biomedical engineering, and again, thought about getting a job afterwards. Actually, I almost took a job at Boeing doing biomechanics on pilots and moving around. But instead, got mad at cancer and made a switch to a postdoctoral fellowship in cell and molecular cancer biology for 5 years. Really, the biochemistry background came in very handy there because I had to become an expert biologist at that time. I got into biophotonics, which is imaging, I'll explain in a minute, and ultimately went to the Fred Hutchinson Cancer Research Center to start working on translational therapies. One of the biggest efforts there was in pancreas cancer, which is something I'll show you again in just a minute, which led me to being an assistant professor here. So all of this turns out to be fairly handy. At the time, all that diverse background in mechanical engineering and biochemistry, it all seemed kind of like a mashup, but it came forward to be what I do now. So we think about cancer as fundamentally a genetically abnormal disease. I just heard Ed talking about mutations and mutations in the tumor and abnormal DNA. So you have that genetic abnormality happening, but how a cell manifests its behavior depends on the environment around it. So I can have one genetically abnormal cell here in the tumor, and it may do nothing its entire existence. It may just sit there. But I may have one over here that grows and multiplies, and I may have one over here that metastasizes. In other words, it moves to a different part of the body. And largely, if those are genetically similar cells, the decision is made by the microenvironment. That environment, just like this room, has chemical signals in it, right? We have oxygen to breathe and gases in the air, and there's chemical things there. But it also has physical properties, just like this floor I can stand on. I don't sink in it, I can run across this room, right? And there's patterns. There's patterns in a tumor. For instance, if I wanted to go out the door in the back corner there, the cleanest path for me to do it would be just to take the straight line. You might not like that as much as I'm doing some American Ninja Warrior dance over the top of you. You might think it's funny, I would think you would. But it wouldn't be so kind to you guys to try to jump and climb over you to get there. Instead, I might have a much easier route by just walking through the path that's already here. Those same kinds of paths exist in a tumor. And those patterns help drive disease and allow it to move. And that's one of the things we study. So thinking about the superposition of all these physical and chemical things, so not just the chemistry, but the engineering aspects of it. Cells exert forces when they move, just like when you exert forces when you walk. Just like you push on a floor, a cancer cell has to push and pull to move through the body. And so can those things be targetable? Can you target the machinery of a cancer cell uniquely to shut it down? And that's part of the questions we study. And fortunately, I'm really blessed because all that unique background has allowed us to bring a multitude of engineering technologies to bear on the problem. So I ended up studying cell molecular cancer biology, and we spent a lot of time using those techniques to do what we do. But then we started thinking about mouse genetics and mathematical modeling and those physical forces and mechanics. So I've been able to be in a position where I can mash up this diverse background of learning to apply to a really unrelenting problem. And I guess that's kind of one of my motivating things to say, is that knowledge can always be applied later. There's sort of no loss of knowing and learning things. You never know when it's going to come in handy. You'd be shocked at how often I'm looking at a cancer problem and something I learned in mechanical engineering 20 years ago comes in handy, right? Knowledge is forever. Hold on to it. This all culminates now into one thing I want to say, which is ultimately all this stuff is great to think about the physics of the tumor and how it works, and it's really interesting, and it's very important understanding, but it also translates to how we might think about treating the disease. And this is one example of it. Where we did preclinical work on a drug that went all the way to phase 3 trial. Along the way, phase 2 trial, there was at least one patient who was completely cured of stage 4 metastatic disease. Good thing I'm on my last slide. On the left side, you'll notice a bar graph that seems to go from red down towards green. Right? What you're seeing there is we measured pressures within a tumor. And inside this tumor, these pressures form. It's much like you're blowing up a balloon. And as you get bigger and bigger, it gets harder and harder to blow up because there's something resisting that pressure. And that pressure holds. What ends up happening inside of there is there's blood vessels in there, and there's so much pressure that they get squished and collapsed. And you can't pump drug through those, so you can't treat those regions of the tumor effectively. So we developed a strategy to alleviate that pressure within tumors, to drop it down towards the normal region, that sort of KC green spot, and allow chemotherapies to move again through the tumor. This is what a normal tumor often looks like in pancreas space. Those little green dots are chemotherapy. The black space are parts of the tumor that don't see any drug. The drug's not there. So even if you kill those cancer cells right around there, these cells over here are going to continue to grow. By getting rid of those pressure gradients, we get to that bottom corner, we can re-expand vasculature and effectively distribute drug. If you look at the panel M, that green is chemotherapy now perfusing that entire region. Okay. With that said, I'll take any questions you guys might have. That's what we work on. That's what we do, sort of what we call cancer bioengineering in today's world. I have on my timer 7:40, so I should have 2 minutes. Is that right? Yes?
Are treatments like that one more specifically targeted to specific types of cancer, or one for those types of cancer?
It's unclear. I mean, yeah, some of those therapies that targeting the tumor microenvironment have been effective with some of the most fibrotic tumors. So far, really the poor prognosis cancers like pancreas and a few others have been the most targeted areas. But many of those therapies are released in early stage trials across at least 4 or 5 different cancers. And typically you end up in the trial targeting the ones that are most frequent or most deadly. So you tend to focus on those and work your way back. Other questions? Yeah. How do you remove pressure in a tumor? Yeah, that's a great idea. So you guys have all had like Jell-O or any kind of thing that kind of creates a gel, right? So tumors secrete a sugar actually from the cancer cells and the cells around it, and when it hits water, it expands and swells. So it's kind of like I'm trying to think of something that you could think of that would extend and swell. Boy, is there any kind of material in our daily lives that you hit water and it expands? I don't know. There's like a sponge or something like that, a very dried out sponge. Great example. You fill it with water and it'll expand. So these sugars get secreted into the tumor and they hit water and things from the blood vessel and they expand, but they have nowhere to go, right? Because there's this huge fibrous network around the tumor. And so as they expand inside the tumor, the pressure builds. It's much like if I had a balloon, for instance, and I had a teleportation device, and I started teleporting in like ping pong balls, right? Eventually, I would get full, and I would keep teleporting them in there, and it would get tighter and tighter, and the pressure on them would get greater and greater, and that's what happens inside the tumor. Yes? Can it explode? Can it rupture? That's a great question. We've never seen anything like that, although there are times where you do see sort of lesions sort of become necrotic and abscess a little bit. So whether it's from those pressures or not, we don't know, but it's possible. One thing that does happen, a gross story, one of my fellow postdocs was doing this. If you excise the tumor and it's under that pressure and you cut it improperly, it can release, including all the goo. And one of my coworkers got sprayed and came running out of the room. So there is enough pressure to send things flying. So always wear your protective equipment in the lab. Yes. Any other questions? One more, and then I'll hand off to do. Well, that time the tumor was totally removed, so that's good news. But I'm not a surgeon, but I suspect if you did something like that in the body, that would be bad to spread that stuff around. So I think you definitely would want to avoid any scenarios like that. I think I'm out of time, but if you guys have any other questions, feel free to hunt me down, send me some emails, and other than that, I'll hand it off to Dave.